So this is the first video. It's on chemistry. So we're going to cover chemical bonds and talk about a little bit about some of the macromolecules that are essential for life. So first of all, cells are made of a relatively few type of atoms. What's an atom? Just a review of chemistry. There's a nucleus and a cloud of electrons. Very often it'll be drawn as electrons circling the nucleus, but that's really not how it works. It's a cloud of electrons with a probability of where they are. These electrons are how molecules interact with each other. There's going to be a number of protons and neutrons equal to the atomic weight. Number of protons dictates the atomic number or which atom you are. So if you have one proton, you're a hydrogen. And then the number of electrons minus the number of protons will dictate your charge. So living things are made of very few number of chemicals. You are 96% carbon, oxygen, hydrogen, and nitrogen. The next couple of things, calcium, sodium, potassium, magnesium, phosphorus, are much, much smaller quantities. And then there are some other things like zinc and gold, and there are things that are in you that are much, much lower quantities. So like I said, the electrons are going to dictate chemical reactivity or how you make bonds. So in essence, you want to get to 8 outer valence electrons. The outer valence electrons are dictated by how many electrons the thing normally has. So carbon normally has 4, nitrogen 5, oxygen 6, and that will dictate how many bonds it's going to make. Oxygen wants to make 2 bonds. Carbon needs 4 electrons to be happy, and so we'll make 4 bonds. And so there are ways to get a full outer valence shell. One is by sharing electrons. The chemical bond is a sharing of electrons. A covalent bond is a sharing of electrons where the electrons spin sometime around one nucleus and then sometime around the other nucleus, and both atoms are happy. There's also another way if your electrons are very loosely held, or the electronegativity is so high that you really need electrons. Well, then there's a chance that you could steal electrons from a neighboring atom. So the further up in the uh, right top corner you are, the higher your electronegativity is, uh, the more need for electrons that you'll have. So fluorine is going to be able to steal electrons easily. So fluorine, chlorine, bromine, iodine, these atoms are going to be able to take electrons from those that are holding it loosely, such as sodium, potassium, lithium. Um, and then, like I said, oxygen also has a high electronegativities, sulfur. So these are going to be high electronegativities, and so they're going to pull the electrons closer to them. So covalent bonds, like I said, are formed by the sharing of electrons when electrons are spinning sometime around one atom and then sometime around another atom, um, and and so both are happy because they've got 8 in their outer valence shell due to the ones they're sharing plus the ones that they have on their own, and so those are covalent bonds. Um, if you need Like I said, oxygen needs 2 electrons. So oxygen could share, like say, like it's sharing electrons with a hydrogen over here and a hydrogen over here, um, form 2 different bonds. You could also form double bonds or triple bonds um, by sharing 2 electrons with the same atom. Um, so this carbon is sharing two electrons, this carbon is sharing two electrons. These carbons have a double bond between them. Um, Things can freely rotate around a single bond, but these double bonds, they're rigid. They have no rotation around them at all. Um, like I said, there's an electronegativity, and so some things are pulling harder on electrons than other things. So this oxygen is pulling harder on the electrons than the hydrogens are. The electrons spend more time around the oxygen. That's going to give it a partial negative charge, and they'll spend less time around the hydrogens. That'll give it a partial positive charge. And so we'll have this dipole moment that's set up with these partial charges. You can also have a full charge if you have that pulling off of electrons. So like I said, chlorine really, really wants an electron. Sodium doesn't need that outer electron as much. It would actually be happier if it didn't have it, so that it can have a full outer valence shell. So if you lose an electron, you will be positively charged. We call that a cation. And if you gain an electron by stealing it from somebody else, then we call that an anion. You'll have a negative charge. And then this negative and positive, they'll be attracted to each other. They'll be attracted to each other actually in 3 dimensions. They, the electrons, or the positive uh, sodium is going to attract chlorines in 3 dimensions. So it'll actually take 6 chlorines to completely shield it from its milieu, and that's how we get these crystal structures. Um, so uh, there are varying strengths to different covalent bonds. Some are stronger than others, depending on how many bonds you have. Double bonds are stronger than single bonds. The covalent bonds are able to have interactions in living things. So this is where it comes into play in the context of cell biology. Is that different amino acids might be positively charged or negatively charged, and those positives and negatives will interact with each other, and that's what allows for the specificity of interactions between proteins. Um, Hydrogen bonds are also very important. Like I said, you have this dipole moment where the oxygen is partially positive, or the hydrogen is partially positive and the oxygen is partially negative. That negative will be attracted to the partial positive on a different hydrogen. So a hydrogen bond is an intermolecular bond, whereas covalent and um, ionic bonds are intramolecular. So we'll have an intermolecular bond between 2 water molecules, and this sets up many properties that are important for life. We'll talk about that in further videos. So, like I said, covalent bonds are much, much stronger than ionic bonds, and ionic bonds are much, much stronger than hydrogen bonds. So why is it that uh, DNA, you have to heat it up to 95 degrees to get it to melt apart? I'll let you pause the video and come up with your own answer. So the reason that DNA requires you to heat it up to quite a bit is because although any one hydrogen bond is weak, in aggregate, DNA has many, many hydrogen bonds that each have some strength to them. So every AT has 2 hydrogen bonds, every GC has 3 hydrogen bonds, and there are millions of A's, C's, T's, and G's. And so these millions and millions of bonds in aggregate make the DNA very uh, stable. So, so some polar molecules are able to form acids and bases, and this is going to end up playing a big role in in how amino acids behave in an aqueous solution. So this acetic acid here, it's got this hydrogen that is just barely hanging on right here, and this hydrogen can fall off at different pHs depending on the circumstances of the rest of the molecule that this carboxylic acid is involved in. And so when that hydrogen falls off, it becomes negative. Adding a hydrogen to the solution that you're in is the definition of an acid. And so the amino side of a protein can act as um, a base. The carboxylic side can act as an acid, as well as many of the R group side chains can also have acid and base properties. And so the pKa of a protein is going to end up being very important. Um, so we want to talk in the next video about some of the macromolecules that are involved in life.